If you close your eyes and picture our solar system, what do you see? You probably imagine a vast, dark and quiet space with the sun glowing steadily at the center, a perfect sphere of golden light. And circling that sun, like clockwork, are the planets. You see the 8 major worlds, each following its own immaculate elliptical path, a cosmic ballet choreographed by gravity. Mercury, Venus, Earth, and Mars dance in the inner circle, while the giants, Jupiter, Saturn, Uranus, and Neptune, trace their wide, majestic arcs in the cold outer darkness. Everything seems predictable. Everything feels stable. It's an image of profound peace, a celestial machine running so smoothly that we can set our calendars by it, predict eclipses to the second, and navigate our own world using the stars as a fixed guide. It's a comforting thought. It makes us feel secure, as if we are part of a grand, orderly design. But that image, that peaceful, predictable clockwork, is an illusion. It's a beautiful, comforting, and deeply misleading snapshot of a single second in a very, very long life. The solar system we see today is not the tranquil kingdom it appears to be. In truth, it is a battlefield, and the planets we call home are merely the survivors. Our system wasn't born into this calm. It was forged in a crucible of unbelievable violence, a chaotic demolition derby that lasted for hundreds of millions of years. The elegant orbits we admire are not the original blueprints. They are the leftovers, the final arrangement after countless worlds were destroyed, pulverized, or thrown screaming into the blackness of interstellar space. What we see tonight is simply the last few players standing at the end of a brutal game. And the chaos, it isn't truly over. That comforting stability we cherish is temporary. The clock is still ticking, and the intricate, delicate balance that holds everything together is slowly, imperceptibly coming undone. In the vast timescale of the cosmos, our peaceful era is just a brief intermission. The violence of the past is also a preview of the future. That entire, beautiful house of cards that is our solar system will, one day, completely and utterly fall apart. So, how did this happen? How do you get from a raging cosmic inferno to the quiet, stable system that allowed life to emerge on this one, small, blue planet? And how do we know that this stability won't last? To understand our home, to truly grasp what our solar system is, we have to wind the clock back. We must journey past the familiar planets, past the formation of the Earth itself, all the way back to the very beginning. And to understand our own beginning, we first have to look away from ourselves. We have to look out into the galaxy and discover the marvelous, bizarre, and terrifying families of worlds that orbit other stars. Because by studying them, we finally learned how solar systems truly work. So, we begin our journey by looking out. Far, far out. Our sun is just one star, a single speck of light in a city of stars we call the Milky Way galaxy. And this city is vast, home to an estimated 200 billion stars, perhaps more. For most of human history, we looked up at those distant points of light and wondered. We asked the great question, are we alone? But there was always a second, more fundamental question hiding just beneath it. Not just, is there life out there, but is this out there? Are there other solar systems? Are there other families of planets orbiting those stars? Or is our little neighborhood, with its 8 planets in their stable, predictable paths, a cosmic fluke, a one-of-a-kind miracle? To answer that, we had to build new eyes. Giant eyes, powerful enough to detect not the stars themselves, but the almost imperceptible wobble they make when an unseen planet is pulling on them. Imagine giant, gleaming telescopes some of the largest in the world, perched 14,000 feet above the clouds on the dark, silent peak of a Hawaiian volcano. From this height, they stare into the blackness, night after night, hunting for new, distant solar systems. And what they have found in the last few decades has completely overturned everything we thought we knew. The marvelous reality is that our solar system is not alone. The galaxy is teeming with planets. We now know that many of those billions of stars have their own planetary systems. Planets, it turns out, come in families, just like ours does. But this is where the comfort of familiarity ends. Because as astronomers found more and more of these systems, a strange and unsettling picture began to emerge. Yes, there are billions of other solar systems, but they are nothing like our own. Most of them are bizarre, chaotic, and frankly, completely frightening. The neat clockwork pattern of our home seems to be a profound exception. What we are finding out there are the true wild ones. Imagine a planet many times the size of our own Jupiter, a monstrous ball of gas, but orbiting so close to its star that its year lasts only 3 or 4 days. It's a world being permanently blowtorched, its atmosphere boiling away into space, its surface superheated to thousands of degrees. There's no way a planet like that could have been born there. It must have moved. In other systems, astronomers find planets on wild, suicidal orbits. They don't circle politely. They shoot billions of miles out into the frozen void and then dive back in, skimming the surface of their star before being slingshotted back out again. We've even found planets that orbit their star in the opposite direction that the star itself is spinning. The sheer diversity of these systems is bewildering. It tells us that the universe is far more creative and far more violent than we ever imagined. These discoveries have rendered our solar system just one type of planetary system out of thousands. It's no longer the standard model. It's just a single, quiet data point in a galaxy full of chaos. This realization is profound. It forces us to ask a new question. Not, why is the universe so orderly? But why is our solar system so orderly when most are not? To answer that, we have to find the one single thread that connects all of them, from the strangest, hottest, most violent systems to our own. We have to go back to their shared origin story, their birthplace. Every single one of them, from the hottest, most violent systems with their suicidal planets, to our own quiet, orderly neighborhood, they all begin in the same place. They are born in the cold, dark, and astonishingly beautiful clouds of gas and dust that drift between the stars. We call them nebulae. When we look at them through our telescopes, we are not just seeing pretty clouds, we are looking at star nurseries. These are the places where solar systems are made. If you've ever seen a picture of the Eagle Nebula, you've seen the pillars of creation. They are magnificent, towering columns of dark gas and dust that rise for light years, like cosmic mountains or the spires of a galactic cathedral. Within these dark folds, new stars are hiding, just beginning to ignite. Or perhaps you've seen the Horsehead Nebula, a ghostly dark silhouette of a knight's chess piece set against a glowing crimson backdrop of energized hydrogen. These places are vast, far larger than our entire solar system, and they are the womb of the galaxy. But for millions of years, these clouds just float. They are in a delicate balance, with their own gravity gently pulling them inward, while the heat and motion of their gas pushes them outward. They are innocuous, quiet clouds. So, what is the trigger? What is the event that tips the scales and begins the process of creation? What scientists have been trying to figure out is what gives that first, necessary push. One of the most likely answers is a sudden, violent shock. Imagine a massive star, generations older than our own, living out its life nearby. After millions of years, it runs out of fuel and explodes in a catastrophic supernova. This explosion is one of the most powerful events in the universe, an unimaginably bright flash that can outshine an entire galaxy. This explosion unleashes a cosmic shockwave, a tsunami of energy and matter that races through space. When this shockwave slams into that quiet, unsuspecting molecular cloud, it shatters the balance. It smashes into the gas, compressing it, squeezing it down into dense pockets. And once that happens, a new force takes over, gravity. In those freshly compressed pockets, gravity is now the dominant force, and it begins to pull, relentlessly. The cloud, or a fragment of it, begins to shrink, drawing in more and more gas and dust from its surroundings. As this vast amount of material falls inward, it begins to spin. Just like an ice skater pulling their arms in to spin faster, the cloud spins faster and faster as it collapses. This spin flattens the collapsing cloud, transforming it from a giant, shapeless blob into a vast, rotating platter. This is the protostellar disk. At the very center of this spinning disk, the material is being crushed into a dense, super-hot ball. The pressure is unimaginable. The temperature climbs, rising from the cold of deep space to thousands, then millions of degrees. It gets hotter and denser until a critical threshold is reached. Suddenly, at the core, hydrogen atoms are squeezed so tightly that they no longer just bounce off each other. They fuse. They merge to become helium. In that instant, a torrent of energy is released. A star ignites. A new sun is born, and it bursts into light, illuminating the spinning disk of leftover material that surrounds it. That leftover disk is the key. It's the afterbirth of the star, and within it, spinning in the light of the new sun, are all the seeds of a future solar system. All the raw materials for planets, moons, comets, and asteroids are right there in that vast, rotating ring of dust and debris. We know this is true because we've seen it. In 2001, the Hubble Space Telescope was scanning the Orion Nebula and took a direct image of a young star surrounded by exactly one of these disks. We were looking at a photograph of a solar system being born. Whenever we see these beautiful images, we are, in a very real way, looking at a baby picture of our own solar system. We looked like that once, 4.6 billion years ago. We were once just a spinning disk of dust. But that, of course, raises the next most difficult question. How do you turn dust into a planet? This, then, was the great mystery. We had a beautiful theory. A star is born, and the leftover material, a spinning disk of gas and dust, eventually forms planets. We had even seen these disks around other stars. But there was a 40-year-old hole in that theory, a problem so fundamental that it stopped the entire process before it could even begin. The problem was the dust itself. How do you get from microscopic grains of dust, smaller than particles of smoke, to a planet the size of the Earth? The obvious answer, of course, is gravity. Gravity pulls things together. That's what it does. But gravity is astonishingly, almost comically, weak. You are experiencing it right now, but you can overcome the entire gravitational pull of the planet Earth with a single hop. A tiny magnet can pick up a paperclip, defeating the gravity of an entire world. Now, imagine two microscopic dust grains floating in space. The gravitational pull between them is, for all practical purposes, zero. If they bump into each other, they should just bounce off or shatter. there is no force strong enough to make them stick together. For decades, our models of solar system formation stalled right here. We had the building blocks, but we had no way to build. And then the answer came. It didn't come from a giant telescope staring into a distant nebula. It came from a place much closer to home, orbiting just a few hundred miles above our heads. The answer, it turns out, was found by accident, inside a floating bag of coffee. The place was the International Space Station. The astronaut was Don Pettit. He wasn't on a grand mission to solve planetary science. He was simply experimenting with the strange physics of weightlessness, something he called his Saturday morning science. He would take everyday items and just see what they did. On this particular day, he was using clear plastic bags, the kind astronauts use for drinks, and he filled them with different particles. One bag had grains of salt, another had sugar, and one just had some leftover instant coffee powder. He inflated the bags, shook them up, and then he just watched. Back in Mission Control, another astronaut, Stanley Love, was watching the video feed, and he saw something that made his jaw drop. The tiny particles of salt, sugar, and coffee weren't just floating aimlessly apart, as everyone expected. Instead, they immediately began to cluster. They were drawn to each other, clumping up instantly into little floating dots. Dust bunnies. They weren't just bouncing off each other, they were sticking. Love reportedly called up to the station, his voice full of excitement. "Don, this is incredible. You've just solved a 40-year-old problem in planetary science." What Pettit had accidentally discovered was the missing first step. In the microgravity of space, where the pull of a planet is neutralized, these other, weaker forces suddenly get to be the star of the show. It wasn't gravity pulling the coffee grains together. It was static electricity, the same force that makes a balloon stick to your hair. In that spinning disk of dust around a young star, the same thing happens. Two tiny dust particles collide, and their tiny electrostatic charges make them stick. Now you have a slightly larger particle. It tumbles through the disk and bumps into another, and it sticks. This is how you build a planet. It's not a single, grand event. It's a slow, patient accumulation. The dust bunnies grow into clumps. The clumps collide and stick, forming small rocks. The rocks collide and merge, growing into boulders. This process continues, getting bigger and bigger until the object reaches a critical threshold. Once a growing boulder gets to be, say, half a mile or a mile wide, it finally has enough mass for its own gravity to take over. And that is when the entire game changes. It's no longer just about accidental sticky collisions. Now this planetesimal, this proto-planet, is a hunter. Its gravity starts to actively pull in everything in its path. It becomes a cosmic vacuum cleaner, sweeping its orbit clean of all the remaining dust and rocks. The bigger it gets, the stronger its gravity becomes, and the faster it eats. It begins to devour other, smaller boulders, growing larger and larger with each collision. This is the moment that mighty planets are truly born from humble dust. This is exactly what happened in our solar system 4.6 billion years ago. And it was not a gentle, quiet process. It was a feeding frenzy. And it was about to get very, very violent. The first phase of creation, that slow, patient clumping of dust into boulders, was over. But the next phase was just beginning, and it would be anything but patient. Our solar system, in its late infancy, did not have the 8 well-spaced planets we know today. Instead, based on our best models, it was a crowded, chaotic place. There were perhaps as many as 100 young planets, or protoplanets, all crammed into the inner solar system. All of them were vying for the same space, their orbits not yet stable, their paths crossing and weaving. This was not a clockwork ballet, it was a cosmic demolition derby. Collisions were not just possible, they were inevitable. It's difficult for us to even imagine what this would have looked like. Try to picture it. If you could have stood on the surface of the young Earth, a molten, blackened world, still hot from its own formation, and looked up, the night sky would have been terrifying. It wouldn't be the empty, peaceful void we see. It would be a crowded sky. You would see other worlds, other planets, some appearing as large or larger than our own moon does today. Some would be glowing red with their own internal heat. And you would see the traffic. The sky would be constantly streaked with fire, as the debris from past collisions, from boulder-sized to city-sized, rained down in a never-ending meteor storm. This was the environment that the survivors had to endure, and it raged for 500 million years. We know this is true, not just from computer models, but from looking at other, younger solar systems out in the galaxy. When we point our telescopes at stars that are in this phase of their life, we don't see neat, clean systems. We see them shrouded in enormous, brilliant disks of dust. But this isn't the cold, primordial dust of formation. This is a hot, fresh dust, generated by the grinding, pulverizing, and vaporizing collisions of young planets. We are, in effect, watching other solar systems tear themselves apart in their own demolition derbies right now. The survivors in our own system all bear the scars of this brutal era. You just have to know where to look. Let's start with the one closest to the Sun, Mercury. Mercury is an anomaly. It's a tiny planet, not much bigger than our moon, but it is incredibly dense. It appears to be almost entirely made of a giant iron core with only a very thin, rocky crust. It's as if it's a planet-sized cannonball with a thin layer of stone pavement on top. This makes no sense for a planet that formed normally. The only explanation that fits is that Mercury used to be much bigger. It must have had a thick, rocky mantle, just like Earth or Venus. But early in its life, it was struck by another massive, planet-sized object. The impact was so catastrophic that it didn't just make a crater. It completely blew Mercury's crust and mantle off, blasting that rock and debris into space forever. What we see today is just the heavy, iron heart that survived. And the young Earth did not escape either. In fact, it was the victim of the single most important collision in our planet's history. Long ago, when the Earth was still a young, molten ball, it was not alone in its orbit. Another young planet was sharing its path, a world we now call Theia, estimated to be about the size of modern-day Mars, and it was on a collision course. Theia didn't hit the Earth head-on. It slammed into our planet at an angle, a glancing blow of almost unimaginable power. The energy released is beyond any human comprehension. It didn't just throw up dust, it vaporized oceans of molten rock from both worlds. A colossal plume of this superheated, vaporized rock, the combined crusts of both planets, was blasted into space. This material didn't escape Earth's gravity. Instead, it formed a brilliant, glowing ring of white-hot debris around our planet, a ring that would have lit up our night sky. Over the next few thousand years, a mere blink in geologic time, the gravity of that ring began to pull it all together. The debris coalesced, clumping into a single, large, spherical body. That body is still with us today. It is our constant companion. We call it the Moon. The moon was born from the most violent collision our world ever suffered. And what about all the other debris? What about the countless smaller planets that were smashed to pieces during this 500 million year free-for-all? Many of them ended up in a belt between Mars and Jupiter. This is the asteroid belt. It isn't, as was once thought, a planet that failed to form. It is the junkyard. It is the graveyard, the leftover shrapnel, the rocky, battered remnants of the dozens of worlds that were destroyed, the ones that lost the Demolition Derby. So when we look at the inner solar system today, at the nice, neat planets of Mercury, Venus, Earth and Mars, we are not looking at the original cast. We are looking at the final survivors. They are the ones who, through a combination of luck and gravity, managed to win the battle, to absorb their rivals, and to finally sweep their orbits clean of the competition. The great chaotic construction was over. The inner solar system at last settled down. But the outer solar system, its story was just about to get very, very strange. So, after 500 million years of destruction, the inner solar system had finally settled down. The survivors, Mercury, Venus, Earth, and Mars, had carved out their territory. The construction phase, at least the violent part, seemed to be over. But when scientists looked at the outer solar system, they found a new, profound mystery. The problem wasn't what was missing, it was what was there. The two giant icy planets, Uranus and Neptune, seemed to be in the wrong place. Here's the puzzle. Planets are built from the material in the disk surrounding their young star. And just like a spinning pizza, there's a lot more stuff, more gas and dust near the center than there is way out at the edge. The inner planets formed from rock and metal. The gas giants Jupiter and Saturn formed farther out, where it was cold enough for them to grab onto immense amounts of gas. But Uranus and Neptune are way out there, in the desolate cold. By all rights, there simply was not enough raw material, not enough stuff, in that remote part of the disk to build two such massive planets. It was a fundamental contradiction. So, what were they doing out there? This problem led scientists to a theory so radical, it sounded like science fiction. What if Uranus and Neptune weren't born out there? What if they formed much, much closer to the Sun near Jupiter and Saturn, where all the building materials were plentiful? And what if, after they formed, something pushed them violently, clear across the solar system, to the dark suburbs where they live today? It's a staggering idea. What force, what engine, could possibly be powerful enough to shove two planets, each many times the mass of the Earth, billions of miles? The answer, it turns out, was the two biggest bullies in the schoolyard, Jupiter and Saturn. Our best models now show that these two gas giants got into a very funny configuration. Their orbits, through pure gravitational interaction, fell into a perfect, repeating rhythm. A resonance. It's believed that Jupiter began to orbit the Sun exactly twice for every one time that Saturn went around. Now, this may sound like a minor, neat little piece of orbital trivia, but its consequences were catastrophic. Think of it like pushing a child on a swing. If you push at random times, not much happens. But if you push at the exact same point in the swing, every single time, the child goes higher, and higher, and higher. The energy accumulates. That's what happened with Jupiter and Saturn. With every pass, their gravitational kicks on each other happened at the same spot, adding up, amplifying their power. This resonance allowed them to yank hard on the entire system, and the whole house of cards went nuts. The combined amplified gravity of Jupiter and Saturn began to pull on the two smaller giants, Uranus and Neptune, slinging them away from the sun like stones from a catapult. As these two ice giants were flung outward, they ploughed through a vast, dense field of icy rocks and debris left over from the formation of the other planets. Imagine a bowling match. The two planets were the bowling balls, and this sea of debris, they were the pins. The pins just went kaplooey, scattered in all directions. Billions of these icy chunks were thrown out, creating the vast Kuiper belt. And that blizzard of rocks that Uranus and Neptune ploughed through, it actually acted like a brake. The constant impacts and gravitational friction slowed them down, just enough for them to settle into the new, stable, but very distant orbits they keep today. The chaos was so extreme, it's even possible that Uranus and Neptune swapped places. Some models show that Neptune may have actually formed closer to the Sun than Uranus, and this gravitational mayhem was so intense that it literally made them trade orbits. Now, this idea of migrating planets might sound completely crazy, but scientists are now convinced it's just the way all solar systems work. And we know this because we have seen the evidence in other solar systems. Remember those bizarre hot Jupiters we found? Those giant planets, bigger than our own Jupiter, but orbiting so close to their star, they are blowtorched to thousands of degrees. There is absolutely no way a gas giant could form in that inferno. It's simply too hot. The only explanation is that they formed far out in the cold, just as our Jupiter did. And then they moved. They spiraled inward, migrating across their entire solar system. This confirmation that planets can and do move has even shed light on a mystery about our own sun. Scientists have found large amounts of the element lithium on the sun's surface. Stars like our sun shouldn't have lithium. Their internal heat destroys it. But gas planets do have it. So, how did it get there? It's a tantalizing clue. Could it be that our solar system also had a migrant? Perhaps another gas giant, one that we've never seen, that spiraled inward long ago and crashed directly into the sun. It would be a violent, spectacular end, and it would perfectly explain the mystery of the sun's lithium. What's clear is that the birth of a solar system is a violent, messy, and migratory affair. Planets are thrown around, orbits are swapped, and some worlds are destroyed completely. But over billions of years, things settle down. The chaos subsides, the survivors find their places, and a stable, orderly system emerges. But here is the final, unsettling truth. That stability is just an illusion, and any planet at any time is always in danger of total annihilation. So, after all that cosmic bedlam, the early Demolition Derby, the great migration of the giants, our solar system finally settled into the arrangement we see today. The chaos subsided, and a semblance of order emerged. But this leads to a critical question. Why is it stable? Why don't the planets just fly off or spiral into the sun? What is an orbit, really? The answer is a beautiful balance of two forces, the sun's immense gravity and the planet's own momentum. Think of it this way, the sun is constantly pulling the Earth directly toward it. We are, at this very second, falling freely toward the sun, but at the same time, the Earth has a tremendous sideways velocity, a leftover from that original spinning disk of gas and dust. We are moving at over 66,000 miles per hour. The result is that as we fall toward the sun, we are also moving so far sideways that we constantly miss it. That continuous falling and missing is what we call an orbit. And our solar system has a very, very fortunate arrangement. The planets are spaced out just right, and most importantly, their orbits are nearly circular. This is what keeps the whole house of cards from falling apart. If our orbits were wild and eccentric, like the ones we see in other systems, the planets would constantly jostle each other, scattering to the wind. Our stable, nearly circular orbits are the reason Earth has had billions of years of relative calm, allowing life to evolve. But this stability is a lie. Or at least, it's a very limited truth. While the planets are on safe paths, our solar system is still haunted by billions of leftover pieces from its formation. These are the comets and asteroids, the cosmic shrapnel, and they are not on stable, circular orbits. Many of them come streaking from the cold outer darkness, diving into the inner solar system. And when they do, watch out. We only need to look at our own moon to see the evidence. Its surface is covered in the scars of giant impacts. Earth has been hit just as much, if not more. Our weather and geology have simply eroded most of the craters. We know, for instance, that a 6-mile-wide asteroid slammed into the coast of Mexico 65 million years ago. It hit with the force of 5 billion Hiroshima bombs, wiping out 70% of all life on the planet. A few more impacts like that, and our story would be over. So, why doesn't this happen more often? With all that debris out there, why isn't the Earth being constantly bombarded? It's because we have a protector. We have a bodyguard. It's more than just another planet. Its gravity is essential for life on Earth. It is the biggest, most massive object in our solar system besides the Sun, the giant planet, Jupiter. Jupiter is, quite literally, the biggest baseball bat in the solar system. Its gravity is so enormous that it acts as a cosmic shield. As comets and asteroids come racing in from deep space, they have to pass Jupiter. Most of them are grabbed by its gravity and unceremoniously knocked out of the solar system entirely. It cleans house, protecting us from the vast majority of impacts. And in 1994, humanity got to watch our bodyguard in action. A comet called Shoemaker-Levy 9 was on a dangerous path, racing toward the inner solar system. But it never made it past Jupiter. Astronomers around the world watched, stunned, as Jupiter's gravity first tore the comet into more than 20 pieces. Then, one by one, those pieces were dragged down, slamming into Jupiter's atmosphere. The explosions were the biggest humanity had ever witnessed. We saw fireballs larger than the entire planet Earth erupting from Jupiter's clouds. Had that comet, or even one of its fragments, hit us instead, it would have resurfaced the planet. It would have been the end of life as we know it. Jupiter took the hit for us. Scientists estimate that if Jupiter wasn't there, in its exact right place, the impact rate on Earth would be something like 1,000 times higher than it is today. We wouldn't just be worried about dinosaurs. Complex life may never have had the chance to begin at all. So here we are, in a fortunate orbit, protected by a giant bodyguard, and living in that perfect, delicate sliver of space, not too hot, not too cold, where liquid water can exist on the surface. It's the perfect combination for life. The question is, if our solar system could create these perfect conditions, could others? So we find ourselves in a very special place. Our solar system isn't just a random collection of rocks. It's an intricate, finely tuned system, a product of both violent chaos and incredible luck. We have a stable, long-lived star. We have a set of planets on stable, nearly circular orbits. We have a giant bodyguard, Jupiter, tirelessly protecting us from the worst of the cosmic debris. And the Earth itself is in the perfect spot. We are just close enough to the sun for liquid water to flow, but not so close that it boils away into steam. This privileged slice of real estate is what scientists call the habitable zone. But you can just think of it as the Goldilocks zone. Not too hot, not too cold, but just right. This combination is what allowed life to emerge, to survive, and to evolve over billions of years into the complex biosphere we know today. But it immediately forces the biggest question of all. If our solar system, through this long, chaotic process, could produce a perfect home for life, could other solar systems do it too? Are there other Goldilocks planets out there waiting to be found? This is the question that drives the planet hunters. They are no longer just looking for any planet. They are looking for another Earth. And in 2005, astronomers made one of the most exciting discoveries yet. About 20 light years away, a close neighbor, galactically speaking, they detected a system of planets orbiting a star called Gliese 581. Now this system is, frankly, quite bizarre compared to ours. The star Gliese 581 is a small dim star, a red dwarf. It doesn't burn as brightly or give off as much heat as our sun. Because of this, its entire planetary system is incredibly compact. The 4 planets we know of all orbit closer to their star than Mercury, our closest planet, orbits the sun. At first glance, this looks like the last place you'd search for life. But because the star is so cool, its Goldilocks zone is also much, much closer in. And that's where things get interesting. We know of 4 planets there. One of them is only about twice the mass of Earth. That's an exciting discovery in itself. A true rocky planet. But that particular one is very close to the star, probably far too hot for life. But then there's another one, a super-Earth, about 8 times the mass of our planet. And this one is orbiting just far enough away from its dim star that it might be in the sweet spot, the habitable zone. This was a profound moment in science. For the first time, we had found a rocky world orbiting at just the right distance where liquid water could exist. And where there is liquid water, there could be oceans. And where there are oceans, there could be life. This is no longer just philosophy. It's a target for observation. This discovery opened the floodgates. In 2009, NASA launched the Kepler Space Telescope, a mission with one single profound purpose: to stare at one patch of the sky and find out just how common Earth-like planets really are. And what it found, along with other searches, has been staggering. We now expect to find hundreds, possibly thousands, of new solar systems. The full diversity of what we might find is a glorious quest. We may find planets covered in water. We may find worlds with methane atmospheres, or planets covered in a thick, tar-like organic sludge. Now just think about the sheer numbers for a second. Our own Milky Way galaxy has, at a minimum, 200 billion stars. Some estimates go as high as 1 trillion. A large percentage of those have planets. And our galaxy is just one. The ones we can see, the ones we can take a picture of, number around 60 billion. And that's certainly not all of them. The math becomes overwhelming. The numbers are too large for the human mind to grasp. Tonight, when you look up at the night sky, even at a patch that looks completely empty, your sight is crossing the path of billions upon billions of solar systems. And if it happened once, here, it's almost a statistical certainty that it has happened again, somewhere else. But as we search for other worlds, we must also look to the future of our own. Because this too shall pass. Solar systems don't last forever. But there is a final sobering truth that underpins all of this. Nothing lasts forever. Not empires, not mountains, not species, and not even solar systems. Ours may seem stable now, a perfect machine that has run for billions of years. But in reality, it is very slowly, almost imperceptibly, coming apart at the seams. That comforting stability is an illusion, a temporary truce in a universe that always, eventually, tends toward chaos. Even now, the planets are not in perfect isolation. They are constantly pulling on each other, a tiny gravitational tug-of-war that spans the entire system. Over a few years or even a few centuries, these tiny nudges do nothing. But over millions or billions of years, these tiny disturbances can add up. They can amplify. The nice, neat, circular orbits can begin to wobble, to stretch, to degrade. The house of cards that is our solar system is still trembling. Computer simulations that run our solar system forward in time show that this future chaos is a very real possibility. In a few billion years, these tiny nudges could be just enough to disrupt the delicate orbit of Mercury. Its path could become unstable, stretching out until it crosses the orbit of Venus. Or, in a truly terrifying scenario, it could be deflected inward, spiraling into the Sun, or outward on a direct collision course with Earth. In other simulations, the planets jostle each other in a gravitational do-si-do, flinging one of their number out of the solar system entirely. Mars could one day be ejected, sent tumbling alone into the blackness of interstellar space. But don't panic just yet. This is a possibility billions of years in the future, and in any case, even if our solar system's internal clockwork doesn't fail, our star has an execution date. There is a catastrophe coming that is not a possibility, but a certainty. The end of our solar system, one way or another, is doomed to come when the star at its center dies. In about 5 billion years, our sun will run out of its primary fuel, the hydrogen in its core. And when it does, it will lose the battle it has been fighting its entire life, the balance between gravity pulling in and nuclear fusion pushing out. The core will collapse, but the outer layers will do something truly terrifying. They will swell. The sun will begin to expand and expand and expand, transforming into a new, terrifying object, a red giant. It will no longer be the life-giving golden orb we know. It will be a monstrous, bloated crimson furnace, so large it will fill our sky. It will be the last thing we ever see. As it swells, it will consume Mercury, vaporizing the tiny planet in an instant. It will then reach Venus and swallow it whole, and then it will be Earth's turn. Long before it touches us, the heat will be unimaginable. The oceans will not just warm, they will boil. The entire planet will be sterilized in a global pressurized wave of superheated steam. The sky will be a ceiling of red fire. The land itself will melt, turning the continents back into the molten rock they once were. And then, the sun's outer atmosphere will reach us. The Earth's orbit will be inside the sun. Our world, and everything that ever happened on it, will be vaporized. We will be toast, vapor, literally. And then, after a time, the red giant itself will fall apart. It will shed its outer layers, puffing them away into space as a beautiful, glowing nebula. All that will be left behind is the star's tiny, dense, burnt-out corpse. It will be a white dwarf, an object about the size of the Earth, but with the mass of a star cooling off slowly over the next 1 trillion years. This faint, dying ember will be the real end of our solar system. But it won't be the end for all of it. The remains of the inner planets will be gone, just a ring of metallic vapor around the white dwarf. But the giant outer planets, Jupiter, Saturn, Uranus, and Neptune. They will live on. They will have been scorched and battered during the sun's red giant phase, but they are large enough to survive it. They will continue to orbit the white dwarf, their tiny dead sun, in a new, profound, and permanent cold. They will be silent, icy sentinels orbiting a graveyard. And this, we now know, is the likely fate of countless other systems all across the universe. So, this is our story. The story of a solar system that emerged from utter chaos to eventually, miraculously, support life. We are the fortunate survivors. An extraordinary and improbable chain of events unfolding over billions of years had to happen in just the right way to make our world possible. We needed the right kind of star, a stable, calm, long-lived sun, perfect for life to slowly evolve around. We needed the right number of planets, in just the right places, at just the right distances from each other, all settling into stable, nearly circular orbits. The Earth itself had to form in precisely the right place, this perfect, life-giving, habitable zone. And the giant planets, the very ones that created so much chaos in the beginning, had to settle into their perfect places to stand guard and protect us from the barrage of deadly impacts. All of that, every single piece of the puzzle, had to fall into place just for life to have a chance. What we see today is not the way things have always been, and it is most certainly not the way things will always be. We are not necessarily unique. It is just the way things happen to work out for us. And this, then, leads us to the ultimate question. Ours is the only planetary system we know, out of all the thousands we've found, that supports life. As solar systems go, does that make us extraordinary? Or does it make us perfectly normal? We don't know the answer, not yet. But we are, for the first time in human history, a species that is actively looking. Every single week, we are discovering new solar systems with new planets. And with every new world we find, we get one step closer to answering that question. It could be that it is just a matter of time before we discover that we are not alone. It used to be that when we looked up at the night sky, the only planets we knew about were the ones right here with us. Our solar system seemed to be the blueprint, a tidy, organized family of 8. But now we've discovered we're part of a much larger, much stranger cosmic neighborhood. We've found rocky worlds, like our own, and massive gas giants orbiting other stars. And they are telling an amazing and sometimes violent story. It is an extraordinary moment in scientific history. For the first time, we know for certain that other planetary systems are out there. And they aren't just there. They are everywhere. They're incredibly common. Let's try to put this into perspective. Our galaxy, the Milky Way, is home to at least 200 billion stars. Think about that number. 200 billion. The data we're seeing suggests that there are dozens of billions of planets out there just in our galaxy alone. The universe, as it turns out, is full of galaxies, gas clouds, stars, and, as we now know, an almost uncountable number of planets. Our solar system, with its familiar 8 planets, is just one tiny group in a vast cosmic family. In 2009, NASA launched a mission to find them, the Kepler Space Telescope. Its entire job, for 6 years, was to stare at a patch of sky and hunt for the shadows of these new worlds orbiting other stars. And what it found, well, it completely rewrote our understanding of what a planet can be. So far, astronomers have catalogued over 400 of these new worlds, and the variety is stunning. Some are colossal balls of churning gas, 5 times the size of our own Jupiter. Just imagine a planet so massive, it makes the king of our solar system look like a lightweight. Others are huge, rocky worlds, super-Earths many times larger than our own home. And then there are the strange ones. Planets that follow wild, erratic orbits, careening through their systems. Some are so close to their parent star that they are literally burning up, their atmospheres boiling off into space. If there's one thing all these discoveries have made clear, it's that no 2 planets are the same. Each one is, in its own way, one of a kind. And this is where the real puzzle begins. Because planets everywhere in the universe are made in the same way. They are the leftovers. They form from the exact same dust and debris that is left over from the birth of a star. So if they are all made the same way, from the same ingredients, what makes them all so different? Why does one star system produce stable rocky worlds, while another produces massive churning gas giants? Why does one world end up a burning inferno and another a frozen rock? This is the question we are going to explore. But to do it, we have to face a challenge. Most of these new planets are, well, they're far away. They're incredibly hard to study in detail. We can't send a probe there. We can't see their surfaces. They are, for now, mostly just shadows and data points. So, to understand how planets work, how they are truly built, how they evolve, and how they become unique, we have to look closer to home. Most of what we know, most of what we're learning, comes from the 8 planets that orbit our own star. They are our laboratory, our family, and by studying them, we can begin to unlock the secrets of the billions of other worlds out there. So, how do you get such drastically different worlds from the exact same starting materials? Well, our solar system, all 8 planets, came from the same single vast cloud of cosmic debris. Every planet, from the rocky inner worlds to the giant outer gas planets, was made from the same stuff. You can picture it as this enormous, swirling cloud of gas and dust that the sun left behind. Now, in the beginning, that cloud was a pretty homogeneous mix. Scientists would describe it as being full of silicates, which is just the word for rock-forming materials, along with water vapor, a whole lot of hydrogen, some methane, and various other elements. If all the planets are made from the same batch of ingredients, why did they end up so different? The answer, it turns out, has a lot to do with baking. The entire solar system was, in effect, a giant kitchen, and the elements in that dust cloud, those were the ingredients for the cake. You had your flour, your eggs, your sugar, all mixed together. But as any baker knows, the final product doesn't just depend on what's in the bowl. It depends on the temperature of the oven. You mix the ingredients, you put the batter in the oven, you apply heat, and it changes. It transforms. This is precisely what happened in our solar system. The sun was the oven, but the temperature wasn't the same everywhere. The closer you were to the sun, the hotter the oven. And just like in a real oven, different things cook at different temperatures. Let's imagine we can fly into that early solar system. Close to the young blazing sun, this is the hot zone. The heat and radiation here are ferocious. This intense heat acts like a cosmic blast furnace. It burns off the lighter, more delicate ingredients. It boils away the water vapor. It scatters the light gases like hydrogen and helium. So, what's left? What can survive that kind of heat? Only the materials that stay solid at extremely high temperatures, things like metals, things like rock. This is the fundamental reason, the first and most important rule, why our inner solar system is home to the rocky planets, Mercury, Venus, Earth, and Mars. They are the dense, heavy survivors of the sun's inner furnace. Now, as you move farther away from the sun, the oven temperature drops. You move into the cold zone, where it's much colder. And out here, as you'd expect, a completely different kind of planet gets to cook. But the temperature is only half the story. The quality of the ingredients matters too. The specific type of cloud a solar system forms in is critical. Think about it. What if your solar system was born from a cloud that was, well, ingredient poor? A cloud that just didn't have enough of those heavy materials to build something like the Earth. In that case, you could end up with a solar system that only has gas giants and no rocky planets at all. So, to get a planet like ours, two things have to happen first. One, you need to be in the right kind of neighborhood, the hot zone. And two, you need a pantry that is stocked with the right ingredients. You need a cloud that is full of metals and rock. So, let's assume we have our rich cloud and we're in that inner hot zone. What's the next step? To build a world, you have to turn the heat down just a little and let the first tiny seeds of a planet begin to form. So we have our ingredients. We're in the hot inner part of the solar system, in a cloud rich with rock and metal. But how do you take that dust and turn it into a world? The first step is that you have to turn the heat down just a bit. As that initial cloud of gas and dust starts to cool, some of the elements in there, the ones with a very high boiling point, start to condense. They change from a gas, a vapor, into a solid. You can picture it like microscopic frost forming, except this isn't frost made of water, this is frost made of minerals. Tiny little mineral grains begin to appear in the cloud. These are the seeds. They are the microscopic starting blocks of a new rocky planet. At first, this process is incredibly slow. Over long stretches of time, these tiny grains start to stick together. You would have one dust molecule and another dust molecule, and they would basically drift, slam into each other, and become one slightly bigger dust molecule. It's a process driven by simple static cling, like a dust bunny growing under your bed. This new, slightly bigger particle would then tumble through the cloud, picking up more and more and more. This slow, patient build-up is called accretion. As these things got bigger, they were no longer just dust. They became, essentially, rocks. Then, rocks slammed into other rocks and formed boulders. Boulders smashed together to form bigger boulders. For millions of years, the inner solar system was a construction site filled with these growing, lumpy masses of rock and metal. But then something magical happens. A threshold is crossed. Eventually, you get something that is big enough, that its gravity is strong enough to take over. This is the moment the game completely changes. Before this, the object was just growing passively, by accidentally slamming into other things. But now, it's big enough that it can start drawing material in. It's not just a rock anymore, it's an infant planet. It's actively pulling material toward itself. So, how big does it have to be? Well, we can actually see a perfect example of this process, frozen in time, in our own asteroid belt. If you look at the asteroid 4 Vesta, it's a fascinating case. Vesta is a large, lumpy rock, about 329 miles across, and it's almost a planet. It's a good indicator of how big a rocky planet has to be. before it can pull itself into a spherical shape. Vesta isn't quite big enough, it just missed the cut. For a growing planet to become round, it has to reach a critical size. That magic number seems to be about 500 miles across. At that point, the object has enough mass, and therefore enough gravity, to literally crush itself into a sphere. Gravity pulls equally in all directions, smoothing out the lumps, creating that perfect round planet shape. But this process creates another change. As these new, round, infant planets keep eating up all the stuff around them, each collision, each impact makes them hotter and hotter. All of that energy from the collisions doesn't just go away, it gets turned into heat. Eventually they get so hot, they start to melt. And now inside this hot, molten ball, gravity begins to do its second job. It begins to sort the materials. This process is called differentiation. The heaviest materials, many of the metals, like iron and nickel, that were mixed into the rock, began to fall, sinking down through the molten mess, descending to form a much denser core at the very center of the planet. And the lighter materials, the lighter rock, the silicates, they did the opposite. They tended to float up, forming a kind of crusty film on the surface. The young planets, they are finally beginning to look like planets. They have a structure, they have a dense metal core, and an outer crust of rock, but they are not safe. They now have to survive a period of utter violence and destruction, a brutal phase that will determine which planets will live and which planets will die. So we have these new, round, molten worlds. They have separated into a core and a crust. They look finally like planets, but they are not safe. In fact, they are now entering the most dangerous phase of their entire existence, a period of such violence and destruction, it's a miracle any of them survived at all. This is the part of planetary formation that is often overlooked. We like to think of it as an orderly process, but the early history of these planets was, as scientists describe it, very, very violent. There was no real blueprint for each of these newborn worlds. They obeyed the laws of physics and chemistry, yes, but the most important things, the events that would define their futures, happened by pure, brutal chance. Let's set the scene. About 4.5 billion years ago, our inner solar system was not the tidy place it is today. Instead, there were perhaps as many as 100 baby planets, or protoplanets, all circling our young sun. They were all sharing the same space, all on overlapping, unstable orbits. It wasn't a system, it was a cosmic demolition derby. Planet hit planet. Most were completely destroyed. This was not the gentle process of accretion anymore, where dust stuck to dust. This was a battle royale. In this chaotic swarm of planetesimals, certain objects began to grow at the expense of all the others. As they got bigger, their gravity strengthened, and they began to mercilessly sweep up all the smaller objects around them. Imagine being on the surface of one of these growing protoplanets. The sky would be in a constant state of terror. The consequence, as scientists calmly put it, would be an enormous, unending bombardment by debris from space. When this chaotic era was finally over, all that was left were just four, very different and very battered, rocky planets. And this is the key. Each planet's unique impact history left its permanent stamp. This is why they are all so different from each other. The destiny of Mars as a frozen wasteland, or Venus as a volcanic hellhole. It wasn't a plan. It was an accident, smashed into them by a history of random collisions. Let's look at the survivors and their scars. Take Mercury. It's a tiny, bleak, super hot world, but it's also bafflingly dense. It has an unusually massive iron core and a surprisingly thin crust. It's almost all core. How does a planet end up like that? Well, one dominant theory is that Mercury didn't start that way. It was likely a much bigger planet, perhaps with a thick, rocky mantle like Earth's. Then, something huge hit it, but it wasn't a head-on collision. It was a glancing blow. Imagine a catastrophic impact at just the right angle, so powerful that it sheared off most of the planet's lighter-weight crust and mantle, blasting that material away into space. All that was left behind was the dense, heavy, metallic core. The young Earth, of course, did not escape. It also took a giant, world-altering hit. Sometime late in its development, another object, something about the size of Mars, slammed into our planet. This impact was so cataclysmic, it ripped an enormous plume of debris out of the Earth's own mantle. This spray of pulverized rock was flung into orbit around the Earth, and over time, gravity gently pulled all that debris back together. It reaccumulated to form what we now call the Moon. Our constant companion in the sky is not a sibling, but a child born from the Earth's most violent trauma. And then there's Mars. Mars also shows evidence of being on the losing end of a colossal crash. When we look at Mars, we see a stark difference between its two halves. The northern hemisphere has a much thinner crust than the southern hemisphere. One theory that has emerged to explain this is that early in its history, the entire northern hemisphere of Mars was whacked by an enormous object, a single impact that blasted a lot of the crust clean off of it. And where did that crust go? It reaccumulated, piling up on the southern half of the planet. So all of these collisions, this Demolition Derby, it did two things. First, it brutally cut down the number of surviving infant planets. And second, it acted as a chaotic delivery service. It brought more ingredients to the survivors. If your planet got hit by a metal-rich asteroid, those chunks would tend to descend and join the growing core. If you got hit by something light or icy, that new material would float about and become part of the crust. After all this, the 4 rocky planets close to the Sun were almost complete. They had their solid, hot iron cores, a layer of liquid iron, and a jacket of molten rock. But their survival was not yet guaranteed. Now, they would have to face a new, invisible, and relentless threat. One that would decide the fate of their atmospheres and oceans. We tend to think of space as being empty, a perfect, silent vacuum. But it is not. The 4 rocky planets, having survived the chaos of their birth, were now sitting in an incredibly hostile environment. Because the space between the planets is not empty at all. It is filled with a constant, invisible storm. This storm is blown out of the Sun itself. The Sun's powerful magnetic fields often clash, triggering gigantic storms that blast a stream of super-hot, highly charged particles out into space, in every direction, at incredible speeds. This is the solar wind. It is a relentless, deadly current of radiation, and we know it's deadly. Astronauts in orbit, even safely inside their spacecraft, have experienced this. When they close their eyes, they report seeing occasional, tiny, bright flashes of light. That flash, that is an energetic particle from the Sun, traveling across millions of miles, passing through the hull of the ship, passing through their skull, and physically interacting with the fluid in their eye. It is a chilling, microscopic reminder that space radiation is serious business. During the Apollo program, a massive solar outburst, a huge radiation storm, erupted from the Sun. By sheer luck, it happened between 2 of the Moon missions. Had the astronauts been in space, or on the surface of the moon during that storm, it would have been a lethal dose. It would have killed them. So this raises a profound question. If space is this dangerous, why are we alive? Why isn't our entire planet constantly sterilized by this radiation? The answer is that here on Earth, we are protected. We live inside an invisible fortress. We have a magnetic field, a protective shield, generated by the very heart of our planet. To understand how this shield works, you have to journey deep inside the Earth. At the very center is the solid inner core. You can picture it as a hard, crystalline ball made of solid iron. But surrounding that solid ball is something even more important. A thick, massive layer of liquid iron. A roiling, spinning, convecting ocean of molten metal thousands of miles thick. This constant churning motion of conductive liquid, spinning with the Earth's rotation, acts like a colossal electrical generator. It's a vast engine, and it transforms the energy of that motion into a powerful magnetic field that emerges from the poles and wraps around our entire planet. Scientists have even proven this concept. They built a 26-ton, 10-foot wide steel sphere. Inside, they spin liquid sodium at high speed around a solid metal core to simulate the conditions deep inside our planet. And when they got it spinning fast enough, it generated a magnetic field all on its own. This field is our bodyguard. It stands between us and the sun. When that deadly solar wind comes rushing in, our magnetic field deflects it. It forces the stream of radiation to flow around our planet, rather than slamming into it. This shield is the single most important reason we have an atmosphere. It's what keeps the solar wind from boiling away our oceans and blasting our world down to a dead, arid rock. A dead, arid rock, a lot like Mars. This is the great tragedy of the inner solar system. Mars and Earth formed in the same way, from the same stuff. And yet today, Mars is a frozen, hostile desert. Its atmosphere is almost gone, just 1% as thick as Earth's. But it wasn't always this way. We know this because we've been there. In 2004, NASA sent 2 robotic explorers, Spirit and Opportunity, to the Martian surface. They roamed for miles, and they confirmed what scientists had long suspected. They found compelling evidence that water, vast amounts of water, was once there. They didn't just find minerals that form in water. They found, preserved in the ancient sand, the unmistakable layered ripples that are only formed by flowing water. Mars was not always a desert. Water flowed. It had lakes. It may have had oceans. And if Mars had liquid water, it must have had a thick, protective atmosphere. We can see it had giant, extinct volcanoes, which means it had a hot interior. It was made of the same iron and rock as Earth, so it should have had a hot, churning core. It should have had its own magnetic shield. So, where did it go? The evidence tells us that early in its history, Mars did have a strong magnetic field. It was probably generated the exact same way as Earth's, but Mars has a fatal flaw. It's smaller than Earth. This is a simple, brutal law of physics. A smaller object, like a small cup of coffee compared to a large pot, loses its internal heat to the cold of space much, much more rapidly. And that is exactly what happened to Mars. Its internal heat, the engine that powered its shield, bled away into the void. That churning liquid outer core, it began to cool. And then, it froze solid. The moment that liquid core stopped convecting, the engine died. The geodynamo stopped. The magnetic field went away. And the solar wind, which had been held back for eons, was now unleashed. With no shield to protect it, The wind slammed into the Martian atmosphere and began, particle by particle, to blast it away into space. As the atmosphere thinned, the pressure dropped, and the water on the surface evaporated, and it too was lost. Mars, a planet that had all the right ingredients, became a cold, barren, dead world. The fates of the 4 rocky planets were now sealed. Their destinies were determined by violence and by physics. But 4 times farther out, beyond the asteroid belt, in the deep, frigid cold of the outer solar system, the sun was baking a very different kind of planet. If we leave the rocky inner worlds behind, if we travel past the orbit of Mars, past the great asteroid belt, we travel a long, long way out. About 500 million miles from the sun, we enter a completely new realm. This is the kingdom of the monsters. Here, we find the 4 gas giants, Jupiter, Saturn, Uranus, and Neptune. These worlds are a completely different class of planet. And as it turns us out, as we look for planets around other stars, these giants, or worlds like them, are the ones we are finding most often. Our solar system has 4 of them. They are gigantic. They are made of gas, and these monsters have no solid surfaces at all. This brings us back to our central mystery. Why? Why, in the same solar system, do you get tiny rocky planets in one area and these colossal soupy atmospheres in another? It all comes back to our kitchen metaphor. It's all about the temperature. In the inner solar system, we were in the hot zone, too close to the oven's heating element for anything delicate to survive. But out here, we're in the deep cold. This is the freezer section of the solar system. This far from the sun, it is so cold that the materials that were just vapor in the inner solar system, they become solid. This is the key. Out here, you don't just have grains of dust and rock. You have snow. This is what astronomers call the frost line. It's the point in the solar system cold enough for water, methane, and ammonia to freeze into solid ice. This changes the construction game completely. Where the inner planets had to be built from only the rare heavy materials like rock and metal, the outer planets had a brand new and incredibly abundant building material, ice. So the process starts the same way, accretion. But instead of just bits of dust clumping together, you have ice snowflakes clumping together. And there was so much of this ice and gas, so much more material available, that the cores of these planets got to be huge. We think the cores of the giant planets grew to be enormous, perhaps 10 times larger than the entire planet Earth. And what happens when you have a core that massive? You get gravity, a lot of gravity. These giant ice and rock cores became the solar system's new heavyweights. They had so much pulling power, they started to act like cosmic vacuum cleaners. They began to suck in all the gas in their neighborhood, specifically the lightest and most common gases of all, hydrogen and helium, the very gases the inner planets could never hold on to. The larger they got, the more gravity they generated. The more gravity they generated, the more gas they pulled in. It was a runaway effect. They just kept growing, building up these thick, soupy, crushing atmospheres tens of thousands of miles deep. This incredible gravity had other consequences. It pulled in and captured vast amounts of debris, giving these planets their own enormous families of moons. Jupiter and Saturn, for example, have over 60 moons each. And that gravity, it also created their most iconic feature. Rings. Now, Saturn, of course, is unique. It's the superstar of the planets with that gorgeous, unmistakable ring system. But here's a fascinating detail. It turns out all 4 of the gas giants have ring systems. Jupiter, Uranus, and Neptune, they have rings as well. It's just that, compared to Saturn's, theirs are really weak and pathetic. They're extremely hard to detect, like a faint charcoal smudge against the black of space. Saturn's rings are the main event. From Earth, they look like a single flat solid disk, perhaps like a vinyl record. But they are not. When we sent the Cassini probe to fly past them, it revealed what they truly are. They are thousands of separate individual ringlets, each only a few miles wide. And inside those rings, we detected billions of individual pieces of ice and cosmic rubble. Some are as small as a grain of sugar, others as large as a mountain, and they are all orbiting Saturn at speeds of up to 50,000 miles an hour. This environment is in constant, chaotic motion. These bits of ice and rock are always crashing into each other. Some stick together, growing into tiny moons. Others are smashed apart, but they never get to form into one large, stable moon. They are too close to the planet. Saturn's immense gravity just tears them apart. So, where did this spectacular debris field come from? Scientists are still figuring it out, but the leading theory is one of ancient cosmic violence. It goes like this. A long time ago, a comet may have smashed into one of Saturn's large icy moons. This collision could have knocked that moon out of its stable orbit, sending it drifting closer to the planet. As it got too close, Saturn's gravity overwhelmed it and tore that moon to pieces. All of that debris, all of those billions of icy fragments, got trapped in orbit. They became the rings. But as beautiful as the rings are, the real mysteries of the gas giants, they don't lie in the rings we can see. They lie deep inside them, tens of thousands of miles beneath the storm clouds. This is where the real action is. It is a place so extreme, it challenges the very laws of nature. So what exactly is going on inside these giant planets? They are, by far, the most common type of planet we are finding out in the galaxy. But they are also the most mysterious. We know Jupiter's dense atmosphere is 40,000 miles deep. We can see the high-speed bands of gas, the violent storms, and the great red spot raging across its surface. But we have no idea what's happening deep inside, far beneath those storms. To find out, NASA launched the Galileo spacecraft on a 14-year mission. And on December 7th, 1995, it did something incredible. It dropped a probe, a tiny, specialized lander, and sent it diving directly into Jupiter's atmosphere at a speed of 160,000 miles an hour. Parachutes deployed to slow it down as it plunged into the thick, swirling clouds. For 58 precious minutes, it transmitted data back to Earth. It detected lightning in the clouds. It measured winds raging at 450 miles an hour. But the most fascinating and terrifying part of the probe's journey is what didn't happen. People ask, what did the probe hit? The answer is nothing. It just fell. It fell continually into the Jupiter environment. It's not a hard planet. It is a bottomless, thick, hydrogen soup. As the probe descended, the pressure just increased and increased and increased. It recorded pressures 23 times greater than here on Earth and temperatures over 300 degrees. Even though this probe was built like a tank, it was never designed to survive this. When you are in a gas giant environment and you go deeper and deeper, that hydrogen soup, that has no solid surface, it still has weight, and eventually you will simply be crushed by the overlying weight of the material that's there. The probe descended for only 124 miles before it was finally silenced. crushed, and then vaporized by the immense pressure. It gave scientists their first real glimpse of Jupiter's interior. But the dark heart of the planet, the core 44,000 miles below, still remains a complete mystery. No probe could ever make that journey. So, how can we possibly know what's at the center? Well, it turns out the planet sends us a clue, a very, very big one. Like the rocky planets, the gas giants have a magnetic field, but these are off the charts. Jupiter's magnetic field is 20,000 times more powerful than Earth's. It is so huge, so incomprehensibly vast, that it stretches all the way to Saturn, more than 400 million miles away. It's the largest single structure in our solar system, second only to the Sun's own heliosphere. And these fields are so powerful, they don't need the solar wind to make auroras. They have huge magnetic fields that create their own beautiful auroras at their poles. And this presents a massive puzzle. We know how Earth does it. Earth has a hot, liquid iron core spinning, acting like a generator. But gas planets don't have hot iron cores. We just established they formed far out in the cold, around frozen cores of dust and ice. So, how do you generate a magnetic field 20,000 times stronger than Earth's without the engine that Earth uses? For decades, this was a complete mystery. We couldn't send a probe, so we had to figure out another way. And we did. Scientists decided to recreate Jupiter's interior right here in a lab on Earth. They did it at the National Ignition Facility in California, using the world's most powerful laser. This facility was designed for one specific purpose: to compress hydrogen to extreme densities and temperatures. Inside Jupiter, the extreme pressure is created by the crushing weight of 40,000 miles of hydrogen gas. In the lab, they do it a different way. They focus 192 laser beams onto a single tiny sample of hydrogen. As the pressure in that sample reaches over 1 million times the surface pressure on Earth, the hydrogen turns into a liquid. But that's not enough. They pushed it further. When the pressure reaches tens of millions of times the pressure on Earth, more like at Jupiter's core, where something truly weird happens to the hydrogen. The pressure is so great that it actually rearranges the hydrogen molecule itself. It's a very basic molecule, H2, but this pressure breaks it, squeezes it, until it is able to conduct electricity. It changes the structure of hydrogen into a metallic form. This is the answer. This is what's happening deep inside Jupiter. The pressure and heat have transformed the planet's core into this bizarre, conductive, metallic hydrogen. Jupiter's metallic core works just like the iron core in the Earth. It's the engine, it's the generator. And that is what's creating the gas planet's gigantic magnetic field. Gravity and heat. They are the great creative forces in planet building, shaping everything from the inner core to the outer atmosphere. But there's one more ingredient, one that has everything to do with how planets and how we turn out. And that ingredient is water. Planets, as we've seen, are not fixed. They never stop evolving. In our own solar system, one planet lost its shield and became a barren wasteland. Another, Venus, heated up and became a volcanic runaway greenhouse from hell. Planet Earth has changed as well, but our story was different. We had a game changer, and that game changer was water. When you look at Earth from space, it is the most striking feature. We see the deep, swirling blue of the oceans, the white of the clouds. It is, after all, the blue planet, so it must be an incredibly water-rich world, right? Not true. This is one of the great paradoxes of our home. At first glance, covered 3/4 by oceans, it seems to be soaked. But in reality, the Earth by mass, is only 0.06% water. That is a stunningly small number. There's some water on the surface, yes, and some water trapped in the mantle. But if you were to compare us to other worlds, the Earth is in fact a relatively dry rock. This creates a massive problem. How did we get this water? We've already established that the inner rocky planets, the ones in the hot zone, all started off dry. They formed in a region so close to the sun that any water would have simply evaporated. And even if they had captured some, let's not forget the Demolition Derby. Those massive, planet-shattering collisions that formed the Earth and Moon. They were so energetic, so unbelievably violent, that any water that had been here would have been instantly vaporized and blasted away from the planet. So, Earth was born dry. It was baked dry, and it was smashed dry. And yet, here we are, with oceans. Where did all this new water come from? It moved here. It was delivered. To find the source, you have to look farther out. You have to look at Jupiter, Saturn, Uranus, and Neptune. Those planets, those giants, have enormous amounts of water locked up inside them. And even more dramatically, look at their moons. The moons of Jupiter, Saturn, and the other giants are, in many cases, at least 50% water. They are giant, orbiting balls of ice. The outer solar system, that is where all the water was. So, how did some of it get to planet Earth? The answer, almost certainly, is that far out in our solar system, there were leftover asteroids and comets, objects far enough from the sun that they could retain their water ice. And for millions of years, a blizzard of these watery comets and asteroids came flying into the inner solar system. And some of them smashed right into Earth. Over the eons, as this bombardment continued, the Earth acquired the water that had been a part of those asteroids. This delivery, bit by bit, comet by comet, is what makes up the mass of water that nearly covers the Earth today. But here is the final and most profound twist in our story. The amount of water that was delivered, that was the luck of the draw. It was pure chance. And it turns out, the amount we got was just right. Think about it. Couldn't it have been the case that the Earth acquired, say, half as much water as it did? What would our planet look like then? Well, the interior of the planet, the mantle, acts like a giant sponge. It's very likely that if we had half the water, the sponge of the interior would have just soaked it all up. The Earth's surface would be nearly, if not completely, dry. A global desert. No surface water would have meant no life. Now consider the opposite. What if we had acquired too much water? What if we had received, say, just twice as much as we currently have? We would be a water world. The oceans would be far deeper. They would be so deep that they would cover all the continents. Even the peak of Mount Everest would be submerged under miles of water. And so you have to ask, if the Earth were completely covered by water, would we have had a planet that was suitable for technological life? Technology requires dry land. It requires the ability to smelt metal, to control fire. It's quite likely, in fact, it's almost certain, that the precise, just right amount of water that the Earth just happens to have is what allowed a technological species like us to spring forth. The world as we know it, it exists because a blizzard of comets and asteroids delivered just the right amount of water about 4 billion years ago. And just maybe, the same thing is happening right now, somewhere else in the universe. So, one thing is for sure, there is plenty of water out there. When you really think about it, this shouldn't be a surprise. The recipe for water is just 2 hydrogen atoms and 1 oxygen atom. Hydrogen is the most common atom in the entire universe, and oxygen is one of the next most common atoms. H2O is, and was always going to be, a very, very popular molecule. Water is everywhere in the universe. And as we are now discovering, so are planets. We are just now, finally, beginning to truly understand the actual diversity that lies out there in the cosmos. Scientists are hopeful that as we discover more terrestrial-style planets, more rocky worlds, it will help us tremendously in understanding how our own inner solar system and how our own Earth evolved. But we have to be honest. So far, of the more than 400 new planets scientists have discovered, none of them look like our world. What we have not yet found, what remains the extraordinary holy grail for humanity, is a planet that is about the same size and the same mass and the same chemical composition as the Earth, orbiting another star. We have not yet found another abode that reminds us of home. But we will keep looking, and we have every reason to be hopeful. We know that there are around 200 billion stars in our galaxy alone, and the estimates are that as many as 40 billion of them could have planets. The numbers are almost too large to comprehend. Billions of planets waiting to be discovered. This is what many are now calling the golden age of planetary discovery. For the first time in our history, we are truly beginning to understand the incredible variety of worlds that the universe can create. It is a fantastically exciting time to be alive. And as we've seen, planets form according to the laws of physics and chemistry. That part is predictable. The ingredients, the location, the heat, those are the rules. But what a planet becomes, its destiny, that has a lot more to do with luck. Was it in a cloud rich with rock? Was it hit by the right asteroid at the right angle? Did it get a moon? Did it form large enough and hot enough to generate a magnetic shield? And did that shield last? And finally, did the comets and asteroids deliver just the right amount of water? Not too much, and not too little. Our own world is a product of all those chaotic, random, lucky chances. And many scientists believe it's only a matter of time before we find another one. Another planet like Earth. One that formed from the same ingredients in the right place, with just the right amount of water and just the right amount of luck.